Up to this point, we have been talking about discrete random variables. And remember, discrete random variables just means that we could list out all of the different options. Now we're going to talk about a continuous random variable. So a continuous random variable essentially means that I cannot make a list of all of them. So I can have a normal set, a skewed set, uniform, bimodal, etc. They all have a mean and a standard deviation. That doesn't mean we would use them to describe those, but they all have those. Examples of when we would use continuous as opposed to discrete. Well, the time it takes to complete a task, because there's an infinite number of times that it could take you to complete a task depending on how precise you were. If we're measuring weight or height or temperature, etc., etc. So a lot of things would use the continuous random variable. Now, if I have a continuous random variable, I have to use the normal model. And so again, they pretty much have to tell me that it follows a normal model in order for me to use that. If it doesn't follow a normal model, then there's really not much that I can do. So here's an example where we're going to try this together. So the times required to pack stereos can be described by a normal model. So again, they're telling me it's normal, with a mean of 9 and a standard deviation of 1.5. So again, you could draw your little picture if you wanted. I'm not going to do it, but that's essentially what we're dealing with. Times for boxing also follow a normal model with a mean of 6 and a standard deviation of 1. So let's look at this. What percent of stereo systems take longer than 12 minutes to pack? Well, then I'm looking at the packing data, which is mean of 9, standard deviation of 1.5. 9, 1.5. I'm going to find a z-score for that because it's normal, and whenever it's normal we use a z-score. So the probability that time is greater than 12 is equal to the probability that z is greater than observed, which is 12, minus expected, which is 9, over standard deviation, which is 1.5. So observed minus expected over standard deviation, which is 2. Now again, notice I'm not going to pull out the empirical rule and try to figure it out that way, because remember that the empirical rule is just an estimation, and I want a better number than that. So I'm going to then find the probability that z is greater than 2, which means in my calculator or using my z-table or using StatCrunch, whatever. That's how I'm going to find this. So in my calculator, if you don't recall, I'm using normal CDF, and then I would do, so again, this is 0, this is 1, 2 standard deviations, and we're saying greater than. So remember, when you're doing this in your calculator, you're doing whatever the left-hand side or the lower limit is, which is 2, then whatever the right-hand side or upper limit is, and remember, I always use that 10,000 number, and then comma mean, which is 0, comma standard deviation, which is 1. That's where I got that number from. Now, if you don't like to use your calculator or you don't have one and you use StatCrunch, don't worry. I'm going to take you through this process in one of the following videos. So the next 3 videos after this are how to do this all in their TI-84, how to do all of this in StatCrunch, and how to do it all in Excel. So don't worry if you don't know how to do it yet. We'll cover that in just a minute. So again, approximately 2.28% of stereo systems will take longer than 12 minutes to pack. Again, I had to use the normal model because I was dealing with a continuous random variable. Now, just to make sure we understand all of that other stuff that we learned this week about combining random variables. So again, I'm using the times required to pack stereos with the mean of 9 and the standard deviation of 1.5. What's the probability that packing 2 consecutive systems takes more than 20 minutes? So again, now I have a different mean and a different standard deviation. My expected value, which is my mean, is that it takes 9 minutes for each one, which is 18 minutes. My standard deviation, I never use that. I always use variance. So I took 1.5 squared, which is the variance. I added that to 1.5 squared, which is the variance. And then I took the square root. That gives me the square root of 4.5, which is 2.12. Now I can find the probability that the time is greater than 20 minutes by using 20, which is observed, minus expected, which is my new expected value of 18, divided by the standard deviation, which is what I found here. then the probability that Z is greater than 0.94 is about 0.1736, so about a 17.4% chance that packing 2 consecutive systems will take more than 20 minutes.